In exercises 1 to 4, find the vector x determined by the given coordinate vector and the given basis b. So here we need to do number 1, 3 also. So we know that x can be represented as, for any x is inside the basis, can be represented as a1 if we have two vectors. So this is a1 b1 plus a2 b2. So now for 1 we have, this is our a0, this is our a1, this is our p1, this is our p2. So x will be equal 5 multiplied by 3 minus 5 plus 3 multiplied by minus 4, 6. So this will give us 15 minus 12, then minus 25 plus 18. So 15 minus 12, it is 3, minus 25 plus 18, minus 7. So x is equal 3 minus 7. Similarly for number 3, here we have a0, a1, a2. This is b1, b2, b3. So our x will be equal 3 multiplied by the first vector 1 minus 4, 3 plus 0 multiplied by the second vector 5, 2 minus 2 plus minus 1 multiplied by the last vector 4 minus 7, 0. So now this will give us 3 plus 0 minus 4, then minus 12 plus 0 plus 7, then 9 plus 0, then minus 0. So this will give us 3 minus 4 minus 1, minus 12 plus 5 plus 7 minus 5, and here we have 9. So our x is equal minus 1 minus 5, 9. In exercises 5 to 8, find the coordinate vector of the x relative to the given bases b, b1 until bn. So here we need to find the coordinate vector. So we need to do from here 5 and 7. So it is given that b1 is 1 minus 3, b2 2 minus 5, and x is minus 2 and 1. We are looking for a0 multiplied by b1 plus a1 multiplied by b2. So x is given, b1 is given, b2 is given. We need to find what is a0, a1, such that x is equal a0 b1 plus a1 b2. So we need to do row operation for p1, p2, and x to find what is a0 and a1. So this will give us 1 minus 3, 2 minus 5, and x minus 2, 1. So doing row operation for this matrix, this one is now in reduced echelon form, will give us this one. So from here we conclude that a0 is equal 8, a1 is equal minus 5. So the coordinate vector is equal 8 minus 5. So similarly for number 7, we have here 3 vectors and here we have x. So we will do row operation b1, b2, b3 and x to find what is the coordinate vector. So 1 minus 1 minus 3, minus 3, 4, 9, 2 minus 2, 4, 8 minus 9, 6. So after doing row operation, we get our matrix in reduced echelon form, which is this one, 0, 1, 0, minus 1, then 0, 0, 1, 3. So from here it is clear that the coordinate vector of x is equal to minus 1, and 3. In exercise 9 and 10, find the change of coordinates matrix from B to the standard basis in Rn. We know that the change of coordinate matrix is the matrix PB, where this matrix is just the columns of the basis B. So for 9, our PB is equal to 2 minus 9, 1, 8. This is the change of coordinate matrix. In 13, the set B is given by 1 plus t square, t plus t square, 1 plus 2t plus t square. Is a basis for B2. Find the coordinate vector of BT is equal 1 plus 4t plus 7t square relative to B. So if our basis is this one, so for any x in the basis B, we can rewrite it as a naught multiplied by 1 plus t plus a1 multiplied by t plus t square plus a2 multiplied by 1 plus 2t plus t square. Now it is given that for bt is inside B, we have bt is equal 1 plus 4t plus 7t square. Now if we compare this one by this one, we see from here that a naught multiplied by 1 plus a2 multiplied by 1 should be equal 1. So a naught plus 2a2 should be equal 1. Then for this one, here we have 4t. So the coefficient of t here, a naught from the first one, plus the coefficient of t here, a1, plus the coefficient of t here, 2a2 should be equal to 4. Now for t square, the coefficient of t square, there is no t square here. The coefficient of t square here, a1, plus the coefficient of t square here, it is a2. So this should be equal to 7. Now if we build our matrix, we have this form. The coefficient of a naught is 1, 1, 0. Then the coefficient of a1 is 0, 1, 1. The coefficient of a2, 2, 2, 1. And then we have this one, 1, 4, 7. So now our matrix is this one. Just we need to do row operation. Sorry for this one. It is a naught plus a2. So this one is a1 also, because here a2 is multiplied by 1, so we have this one. So now if we do row operation for this matrix, we get our new matrix is 1 0 0 0 1 0 0 0 1, and here we have 2 6 minus 1. So from here we get the coordinate vector of BT is equal to 6 minus 1. This is for 13. We'll do the same thing for 14. So for 14, for any x in B, it can be represented as a naught multiplied by 1 minus t square plus a1 multiplied by t minus t square plus a2 multiplied by 2 minus 2t plus t square. It is given that our bt is equal to 3 plus t minus 6t square. So now also we can build as this one. We can build a system. So from here it is clear that a1 plus 2a3 is equal to 3, and then a2 minus 2a3 is equal to 1, which is the coefficient of this one. Then here for minus 6 we have minus a1 minus a2 plus a3 is equal to minus 6. So if we build our matrix, it will be 1, 0, minus 1, then 0, 1, minus 1, then 2, minus 2, 1, and here we have 3, 1, 6. So if we do row operation for this one, here I start by A0, A1, A2. This one is A1 until A3, so I need to change this one to not confuse. So this one A1, A2, A3. That's why here we have A1, A2, A3. So now after doing row operation for this matrix, we get it is in the reduced echelon form 1, 0, 0, 0, 1, 0, 0, 0, 1, and here we have minus 17, 21, 10. So from here, our coordinate vector of the BT is equal to minus 17, 21, and 10. In exercise 15 and 16, we need to mark each statement true or false, justify your answer. Unless the stated otherwise, P is a basis for a vector space V. A, if X is in V, and if B contains n vectors, then the P coordinate vector of X is in Rn. This one is true since we represent X as X is equal A0 multiplied by B1 plus A2 multiplied by B2 and so on. So X contain an entry, so that means X is in Rn. If the change of coordinate matrix, which is this one, then the coordinate vector of X is given by the matrix multiplied by X for X in V. This one, it is false. It is equal to P inverse of this one multiplied by X. Now for C, the vector space B3 and R3 are isomorphic. This one is false. B3 and R4 are isomorphic, not R3. Now for 16a, if B is the standard basis for Rn, then the B coordinate vector of X in Rn is X itself. We said this one is true, so this one here false for C. Because, for example, if we have let X, for example, is equal to 5. If we have a basis which is a standard matrix, so our basis is equal E1, E2. Now to represent X as a linear combination of B, so this is equal to 2E1 plus 5E2. So this is as 2 multiplied 1, 0 plus 5 multiplied by 0, 1. This will give us the vector 2, 5. So X and the B coordinate vector of X are equal. This one is true. Then B, the corresponding B coordinate vector of X to X is called the coordinate mapping. This one is false. It should be from X to the coordinate vector X. In some case, a plane in R3 can be isomorphic to R2. This one is true when R3 goes to the origin. So if the plane passes through the origin, the plane is isomorphic when the plane passes through the origin. So this one is true. In 17, the vectors v1, v2, v3 span R2, but do not form a basis. Find two different ways to express 1, 1 as a linear combination of v1, v2, v3. That means we need to solve the matrix v1, v2, v3, and the vector 1, 1. So that's mean 1 minus 3, 2 minus 8, minus 3, 7, and the vector 1, 1. So after row operation, we have 1, 0, 5, minus 5, 5, then 0, 1, 1, minus 2. So from here it is clear x1 is equal 5 x3 plus 5, and x2 is equal minus 2 minus x3. So now if we choose, for example, x3 is equal to 0, then we have x1 is equal 5, x2 is equal minus 2. So from here that's mean 5 v1 minus 2 v2 is equal 1, 1. If we choose, for example, if x3 is equal to 1, then from here we get x1 is equal 10 and x2 is equal minus 5, or x3 is equal 1. So that's mean 10 v1 minus 5 v2 plus v3, this is equal the vector 1, 1. You can choose any value for x3 and here and here. In 27, use coordinate vectors to test the linear independence of the sets of polynomials. Explain your work. So we need to use the coordinate vectors. First, let us construct the matrix. So the matrix, we will take the coefficients of here we have 1, then the coefficient of t is 0, coefficient of t square is 0, coefficient of t cube is 2. Similarly for this one we have 2, 1, minus 3, 0, and for this one 0, minus 1, 2, minus 1. And we'll do row operation for this matrix. We'll get the new matrix or the matrix in reduced echelon form, which is this one, 0, 0, 0, then 0, 0, 1, 0. Now since our matrix has 3 pivots, that means a pivot in each column, so the set is linearly independent. So here use the coordinate vector to test the linear independence of the set. First we will take the coefficients, so the coefficient of constant, then coefficient of t, t square, t cube. We see here we have pivot in each column, so we conclude that the set is linearly independent. In 31, use coordinate vectors to test whether the following sets of polynomials span B2. Justify your conclusions. We know that the B2 polynomials, B2 is isomorphic to R3, so we can write the matrix for this one. So our matrix will be 1, minus 3, 5, then minus 3, 5, minus 7, then minus 4, 5 minus 6, then 1, 0, minus 1. If we do row operation for this matrix, we get the new matrix which is in echelon form, 1, 0, 0, minus 3, minus 4, 0, minus 4, minus 7, 0, and 1, 3, 0. So now this matrix has a pivot in the first column, pivot in the second column, and there is no pivot in the third or fourth column. So no pivot also we have a pivot in the first row and the second row, and no pivot in the third row. So it is not span R3, and by the isomorphism between R3 and B2, the given set does not span B2. So let us write here no pivot in each row. So it is do not span R3, and by the isomorphism between R3 and B2, the given set does not span B2. Now for part B, similarly we need to check this one, so we need to construct a matrix, then we need to do row operation. So B, we'll take the coefficients, so the matrix will be 0, 5, 1, so 0, 5, 1, then 1, minus 8, minus 2, then minus 3, 4, 2, then 2, minus 3, 0. If we do row operation for this matrix, we will get the matrix 1, minus 2, 2, 0, then 0, 2, minus 6, minus 3, then 0, 0, 0, 7 over 2. So let us rewrite this one here. We have minus 3 and 7 over 2. So now for this one we have here a pivot in the first row, in the first column we have a pivot in the second row, second column we have a pivot in the third row, fourth column. So a pivot in each row, that means it is span R3. So the original 4 columns span R3, and by the isomorphic between R3 and B2, the given set span R2, span B2. So we have a pivot in each row. So that's mean the original 4 columns span R3. So by the isomorphic or by the isomorphism between R3 and B2, the given set span B2. In 32, let b1 is equal 1 plus t square, b2 is equal t minus 3t square, b3 is equal 1 plus t minus 3t square. Use coordinate vectors to show that the polynomials form a basis for b2. First, let us construct our matrix. It will be 1, 0, 1, then 0, 1 minus 3, then 1, 1 minus 3. If we do row operation for this matrix, we'll get 1, 0, 0, 0, 1, 0, and 1, 1 minus 1. It is clear we have a pivot in each row, so this one is span R3. And the matrix is invertible, so the original 3 columns vector form a basis because it is linearly independent, has a pivot in each column, and span R3 because we have a pivot in each row. So the matrix is invertible. This means the original columns vector form a basis for R3. Now, by the isomorphism between R3 and B2, the corresponding polynomials form a basis for B2. So, by the isomorphism between B2 and R3, the corresponding polynomials form a basis for B2. Now for part B, consider the bases B1, B2, B3 for B2. Find Q in B2 given that the vector, the coordinate vector of Q is -1, 2, 2. So if we have this one, that's mean Q will be equal -1 multiplied by B1 which is the coefficient of B1 101 plus 1 multiplied by the coefficients of B2 which is 0 1 minus 3 plus the coefficient 2 multiplied by the third vector which is 1 1 minus 3. So from here we get 1 3 minus 10. So QT is equal 1 plus 3t minus 10t squared. So this is our QT given the coordinate vector of Q is -1 1 2. Just we need to multiply -1 by the first polynomial plus 1 multiplied by the second polynomial plus 2 multiplied by the third polynomial, we get this one.